Hey guys, welcome back. I haven't seen you for a while. I haven't made a new video in a while, but we will be finishing out this unit together. So hopefully these last videos I'm going to be making are better than the ones that I made last year. So we've got about 5 more lessons in our last unit before we're ready for the AP test and getting ready for the AP test. This unit will be about comparing counts. So in the beginning of the year, we looked at categorical data and sorting categorical data, which is like what fits in buckets or categories, across a contingency table, which is basically sorting it across multiple variables. So for instance, in the example of the Titanic, which we'll look at tomorrow, I believe, we looked at whether or not what class you were in and whether or not you survived. So survival, status, and then whether or not what class you were in. And we often want to know, is there an association between these two? And so we compare the counts of what we would expect to the counts that we actually got, and that's where we get the name comparing counts. And we can actually quantify that with a p-value using chi-squared statistics, which is what we'll be getting into here. So very common things. I actually saw this, one of the first things I saw in statistics was from a biology class where we did a chi-squared statistic, and so I thought it was kind of cool because I always like crunching numbers, but very common applications that you'll see in this stuff quite often. So but when we were trying to see if there was an association, we compared it to what we expected, and if the probabilities were slightly different, maybe within 5%, we were like, yeah, it's weak evidence, strong evidence, but it really depends on the sample size, and we needed to be able to quantify those with some p-value, which we'll actually learn how to do today. So Fortune 500, Fortune 400 executives, so we compare the zodiac signs of those. Zodiac signs are essentially just basically what month you're born in or something similar to that. So of the Fortune 400 companies, they were able to collect the signs of 256 of those, and we're assuming that if our null hypothesis in this case would be that the signs were evenly distributed among the executives. So there was no sign that was more common than any others, or we would expect that they would vary from sample to sample, of course, so there are going to be some that are more common than others, but that just occurred by chance. Not that there really is something like one sign tends to be more successful in business, and so they rise up to leadership roles and executive roles or something like that. Okay, so our alternative hypothesis would be that there is an association between the birth signs and the executives. So if they are independent, remember we're calculating a p-value, which is a condition probably based on the condition that the null hypothesis is true. So if they are actually independent of each other, then what's the probability of observing the counts that we observed here in this table here? So first of all, what would we expect for each cell? Well, if there were 256 birthdays that we got all together, we divide that by 12. If they were evenly distributed, we would expect them all to be the same, which would give us an average of 21.3 for every single cell. Now, Aries, for instance, had more than we expected, and we will never have a third of a person, so there's always going to be some sort of difference, but there's no reason to round this value for the counts. The expected value will keep them exact. And Gemini was less than expected. It looks like the one that was the most unusual would be Pisces. So Pisces had 29, which would be 8 2/3 more than we expected. Now that could have just occurred by just normal sampling variation. And how would we come up with a p-value for just that one specific one? So we could test the hypothesis. Are executives in the Fortune 400 companies more likely to be Pisces than something else? We could test that. And so basically we do a one proportion test. So we're going to go to test, a one proportion z-test. It's not a t-test. Well, that would be proportion, but one sample t-test would be with means, but these are actually proportions. So our hypothesized proportion would be 1/12. And so I think that's 0.08333 repeating. And then we observed 29 out of a total of 256, and we're going to test a one-sided that it was greater than the null that was expected. All right, so that would give us a p-value of 4%. So our proportion was 11.3. Our sample proportion was 11.3% when we would have expected 8.3%. 8 repeating 3%. And so the p-value, if there really was no association between them, they were independent, evenly distributed, the fact that we found 8 2/3 more than expected would have only occurred in 4% of all samples. So that is pretty rare. That would be enough to say that there's an association, but we really have not just this one thing in Pisces, we really have all these others, and we can't run a one proportion interval or one proportion z-test for all 12 of those. That would be kind of ridiculous. All right, so running a one proportion z-test, if we did that for Gemini, for instance, that would be, it's basically a binomial distribution. So I could graph out the binomial, how many we would expect, and then we had 18, which is less than we expect, a p-value of 26.7. Now, the z-test is using z or z-scores as in like a bell curve, so it's going to be slightly different than what I use for the binomial, but I went ahead and used binomial because it's exact. And then for the Pisces, we already talked about that. We get a little bit higher if we use the binomial because the z-score model is not going to fit it exactly. It will as we go to infinity. It's good enough, but that's why there's a little bit of discrepancy here in what I got on the last slide. Okay, but keep in mind we're running a chi-square test. We're doing all of these tests all added together, so the grand sum total, and see whether or not we think that's that unusual. So the chi-squared goodness of fit test, it kind of sounds like bad grammar, but that is what it's called, or GOF, goodness of fit test. Basically asks how closely does our counted data compare to our expected null model. So here we have a bar graph of all of the signs, and the 21 1/3 is going to be this gray line here. That would be basically evenly distributed across there. Now there is variation, obviously. Some of these are higher than expected, some of them are deficits or less than we expected. If we add up all these deviations, just like standard deviations, honestly, we'll treat them very similar to it, but if we add them all up, then we'd have a sum of the deviations of 0. That's because for every one that's positive, we have one that's going to be negative, because that's how we get the average in the first place, because they all have to add up together to be the 268 or whatever that we had. So what we end up doing with these deviations, just like calculating standard deviation, is we square them so that the negative ones become positive, and so they don't just end up canceling each other out when we take the sum of them. So there'll be a process that we're going to do for the chi-square test that's very similar to the process that we did for calculating the standard deviation. Okay, so here's a table, and this really summarizes the process. And so for today, we're going to be actually filling in these tables so that you can see the process step by step for this data. So first we have our observations. This is going to be all of our counts. We'll put that in list 1. And then in list 2, we have the expected values. So the expected value for all of these is going to be 21.33. Now in the goodness of fit model, they don't all have to be the same. It's very common to say that they're evenly distributed, but they don't necessarily have to. You can actually compare with the goodness of fit model to any expected values. So we'll get into more examples of that later. The residual is just simply going to be the observation minus the mean. So if it's positive residual, it means it was more than we expected. If it's a negative residual, it means it was less than we expected. So I kind of color coded those for you. You saw that graphed out on the last one. And then the next step we do is going to be to take the squared, the deviation squared essentially. That's going to make all these values positive, whether they were negative or they were positive. To start out with, they're all going to become positive now. Then we take the sum of then we find the component, and so each one of these, the squared deviations, kind of has to be scaled in proportion of what we expected. So the larger value we're expecting, then the less that large deviation is going to be as important, because they were larger values to start out with. So basically we find the component of the chi-square statistic by dividing our deviation squared divided by the expected amount, which would be the 21.33. All right, so that's how we find the component. And when we take all the components and we add them all together, the components of the chi-square statistics are going to give us a sum total of 5.0994. Now think of the sum of the components, or this chi-square statistic. So that would be the chi-square statistic. Think of it similar to like a z-score, but it's not like a z-score for it's not like a z-score for like a bell curve. It's a z-score for a completely different set of models, which is going to be our chi-square models. Now, the last thing we can do, this is actually similar to variation, the way that we calculate it. If we take the square root of it, it'll give us a standard residual. Now, the standard residual actually is a z-score. So the square root of this, for instance, would give us 1.66. So this is kind of like the variation for that cell, and this is the standard deviation for that observed outcome, which is 1.66. Now 1.66, if we put that on a bell curve, essentially that would fill in very similar to the value that I got for the binomial, because those are just z-scores. So if I go to second distributions and then we go down to the normal CDF, I'm going to basically just go to negative 1.66, because that'll give you the same value anyway. and it's a standard normal because we're using z-scores. That's going to give me a very similar value, if you notice, to what we got from the binomial, and it's exactly the same value that we got from the 1 proportion z interval, which I did back here. So it is exactly that same value. Let me show you that real quick. Or it's close. That's probably because this was a rounded value, but it's really, really stinking close. Okay, so that is what's going on. That's how the math is working out. So we'll revisit this later again. All right, so if I graph it out, there was one thing we need to know is going to be our degrees of freedom. So the degrees of freedom is always going to be one less than the number of cells that we have if it's just one variable. So we had 12 cells, so that's going to be 11 degrees of freedom. So the mode is going to be 2 less than the degrees of freedom, and then the mean, the average, is going to be our degrees of freedom. So the average here is 11. 2 less than that is going to be 9. That's going to be the most common. So if the mode is always off 2 from the mean, then that means our distributions will always be skewed. So like the mean got skewed towards the right because the tail is always going to be the right. So chi-squared models or family models like the t distributions are always going to be skewed towards the right with that rule. So the degrees of freedom is going to be the mean, and then 2 less than the degrees of freedom would be the mode. So the further we get out there with basically the more degrees of freedom we have, the less that this difference of 2, this offset matters, but they're all still going to be skewed to the right. So the sum of the chi-squared, or the chi-squared statistic that we had, was 5.094. That's the sum of all the components, by the way. That's just this part here. Now that value is less than our mode and less than our mean of our degrees of freedom of 11, or the mode, which is 2 less than that. And so obviously this is going to have a p-value that's very high. It's not going to be statistically significant. It would have to be above like 22 for that. So basically the variation would have to be above 22. And so this is obviously not statistically significant. So even though we could have broken it down to see statistically significant like for Pisces, but when we put it all together, the sum of all of it together was not statistically significant. All right, so assumptions and conditions for chi-squared test. The first one is that we have to have counted data. So we can deal with proportions, but we'd have to multiply them by our sample size to get the actual numbers or counts. So it is similar to proportions, but if they give it to you like with a frequency or anything like that, or a frequency table, we need to make sure that it is actually counts. So the number of each in each cell. All right, so we were given the counts for the number of executives in 12 categories, so we're good to go. Independence assumption. So randomization makes independence more plausible, helping us avoid bias. In this case, the birthdays of executives should be independent of each other. It wasn't necessarily random. They didn't say it was a random sample, but we're not trying to generalize to a larger population. So we're only talking about the 400 Fortune 400 companies. We're not trying to say that that's representative of all other companies or executives or anything like that. So there are 2 parts that we do if we're trying to generalize it to a random to a large population. That would be that it was a random sample. So because we're not trying to generalize beyond the 400 Fortune 400 companies, we don't have to worry about it being a random sample of them. And then we are clearly sampling more than 10% of the 400 companies, and so that we would have violated 10% condition, but again, we're not trying to generalize beyond the Fortune 400 companies, so we don't have to worry about that either. Expected cell frequency. So this is similar to our success failure condition for proportions. We have to make sure that we have enough successes for us to be able to do our Z models and our inferential statistics and stuff like that. So we have to make sure that we have at least 5 counts in each cell, or we're expecting at least 5 counts in each cell. All right, where we were expecting 21.3, which is more than 5 for all the cells. So here's a chi-squared model. This kind of gives you, with degrees of freedom of 5, 10, and 15, you can see how it kind of morphs and changes, and it becomes less skewed as we get higher and higher, because the difference, the offset of 2 of the mean and the mode is going to become less significant the larger our degrees of freedom are, but the smaller it is, definitely the more heavily skewed it's going to be. So this is a chi-squared model. Just some general things. The mode here is always 2 less than the degrees of freedom, so that's going to be the most common. So that's 3 because the degrees of freedom was 5. This is going to be 8 because the degrees of freedom was 10, and this is going to be 13 because that was 15. Now the mean, the balancing point, so this is where the balancing point of the distributions really is going to be is always the number of degrees of freedom that we had in it from our test. So since the mean is always to the right of the mode, the models are always skewed to the right and become less skewed with increasing degrees of freedom because that offset of 2 is less and less important. So here's some more that you get. These are the degrees of freedom. That's our parameter for the chi-squared test. So it's a chi-squared sub k, which is degrees of freedom. And so there you go. You got some really funky stuff. Having 1 degree of freedom, I don't even think it even makes sense, because I don't know how you'd have 0 cell or 2 cells. You're just comparing 2 cells. So I guess it makes sense. Anyway, so yeah, you could have that. That looks like an inverse model. And then we have 2 degrees of freedom, 3, 4, 5, and then 6 degrees of freedom, or 6 and then 9. They skip some there. Anyway. All right, so the chi-square statistic can be used to test whether observed counts in a frequency distribution or a consistency table match the counts we were expecting according to some model. Chi-square statistic is calculated as we did here. It's the sum of all the components of the chi-square test. So we take our observations minus the expected amounts to get the residuals, square the residuals, take this, and then we take the squared residuals and divide them by the expected value to kind of, not necessarily standardize it, but basically to make it into something similar to variation. Then we take the sum of all of those together to get our chi-square statistic. And if we took the square root of all of these components, that would be like going from variation to standard deviation, which would give us essentially z-scores, and they would be z-scores telling us which one of these components was the most unusual, or which one contributed to us being able to reject that null hypothesis the most. In this case, Pisces obviously was the most unusual one. All right, so the standard residual is basically where we take the square root of the components themselves, giving us a z-score of 1.66. Ready? We standardize residuals in a similar manner to the z-score standardized the standard deviation from a mean. Amazingly enough, the residuals follow a normal model. Of course, are you really that surprised? And the standardized residuals follow a standard normal model of 0 and 1, standard at 0 with standard deviation of 1. Therefore, we can think of the unusualness of the standard residuals in the light of the empirical rule. In other words, to think of them as if they were z-scores, because they are z-scores. Okay, so we need to talk about degrees of freedom. So degrees of freedom is the parameter that we have for the chi-squared statistic test. The degrees of freedom is always going to be 1 less than the number of rows multiplied by 1 less than the number of columns. Now, for our example here, we had 12 rows altogether. So let's assume that we take a sample and we know that we have 256 altogether in the sample. So degrees of freedom essentially is telling us how many we need to figure out were Aries, Taurus, Gemini, Cancer in each one of those cells until we can basically figure out the last cell, because by default it has to be whatever's left over. So if I go through and I sort them all and I put all of these for the first 11 cells and I had a total of 227, I can figure out there had to be 29 Pisces left over because of the total number of people that I sampled in the first place. So the degrees of freedom essentially is telling you how many places can we sort them until the last one is pretty much fixed, and we can figure out what that is because we know the marginal distributions. Now, 1 less than number of rows times 1 less than number of columns just means whenever we sort, like for independence state, for a chi-squared test for independence, we're going to have like multiple variables, like for instance the Titanic, where we have four columns and 2 rows, and so it would be 1 times 3, which is just 3. So there's 3 degrees of freedom on that one. So once we know 3 cells, we can basically fill in the rest of the cells based on the information that we knew, because we know the marginal for all of them. Okay, so that's what degrees of freedom is. So the degrees of freedom for a chi-squared test is dependent on the table dimensions, not on the sample size. So that is important. What that means is that increasing the sample size does not actually change the shape of the model. It only helps us gather more evidence to be able to reject the null hypothesis, therefore increasing the power of the test. But there is something that's kind of unusual that happens here. With a large enough sample size, we could reject any distribution of counts because no distribution would fit a model exactly. So sample sizes can actually be too large. So at some point, if you have too large of a sample, you would be able to reject pretty much anything because it's parameterized by the degrees of freedom, not by the sample size. And so the sample size doesn't actually affect it as much. And so it's a really weird thing, but just keep in mind, you can, with a large enough sample, you can say there's an association between anything. So, kind of scary, right? So again, even when we're able to say there's an association, correlation is not always equal causation without a carefully designed experiment. So just don't go too far with it. Just be careful is what I'm trying to say. There's different types of chi-square tests. The goodness of fit model is pretty simple. Basically, we're comparing whatever counts we have to some expected model. They could all be the same, or they could be different values. such as a dihybrid cross, like in genetics and stuff like that in biology. But we'll get to that later. We also have tests of homogeneity or homogeneity, and we have tests of independence. So these are very, very similar tests, and like all these tests are pretty much done the same way, with observations minus the expected values, then we square them, then we add them all together, and then standardize them, and then all that stuff. Okay. A test of homogeneity is whenever you're comparing two different samples. So for instance, if we want to compare students at Pump City North and students at Pump City High, those are two different samples, and we would compare the counts between the two to see if they're homogeneous, meaning they're the same. Independence is from one sample that was sorted across multiple variables, just like the Titanic. So if we want to see if this variable is associated with this variable, not comparing two different samples of like two different populations like PC North and PC West or anything like that, but from the same sample sorted across multiple variables to see if the variables are associated. So the way that we do the tests are exactly the same. It's just a matter of wording. And so don't get too caught up on this one. You could always just call it in the AP test just the chi-squared test and leave out the part of it being a test for homogeneity or a test for independence. So you can probably get away with that anyway. So. All right, example 1, chi-squared goodness of fit test. In a local school, vending machines offer a range of drinks from juices to sports drinks. The purchasing agent thinks that each type is equally favored among students buying drinks from the machines. So we're assuming that they're all equally distributed, that there's no preference for any of them. They could have specified what they thought the ratios were, but they didn't. They thought they were all the same, so that it's still a goodness of fit model. So we're going to put this data into our calculator. So we're going to go to stat and edit, and I got a bunch of stuff already in my calculator, so I'm going to clear that out. So second memory, let me try that again. So second memory, clear all list. Okay, so in list 1, I'm going to put all of my counts, which is 159, 198, 174, and then 149. Okay, and there's just 4 of them, so we would have 3 degrees of freedom, because once I know 3 of them, I can figure out the 4th one, regardless of what that was. All right, so those are my frequencies. Now, for list 2, that's going to be the expected amounts. So that's going to simply be 680 divided by 4, and that's going to be the same for all of them. So I'll do 170, and then 170, and 170. Okay, and then for list 3, that's going to be the residual. So for it, what I'm going to do is go up to list 3 and define it as list the observation minus the expected. So that's going to be list 1 minus list 2. Then hit enter. Okay, so we had 11 less than expected, 28 more than expected, 4 more than expected, 21 less than expected. Now if I take the sum of all the residuals, that's going to give me 0, because that's how the average works. But so what we have to do is square them. So for list 4, I'm going to define that as list 3 squared. So list 3 and then square it. Okay, so now they're all positive values, and then we're going to find the components. So we need to kind of like standardize them, but basically proportionalize them is probably a better way of saying it. So what are those squared deviations in proportion to the expected value? So this is where it does change, where the larger our sample is, the larger our expected value. So it kind of comes into play, but not as much as we wish it did. So for list 5, we're going to take list 4, so second 4, and we're going to divide it by our expected values, which is going to be list 2. So I could basically type in 170 if I want. But I'm going to go ahead and do it as list 2, because sometimes the expected values are not all the same thing. All right, so there we go. Now those are the components. Now the components are the components the components of our chi-squared test. And so when we take the sum of all those components, that's going to give us our chi-squared statistics. So that was list 5, right? While I'm here, I'm going to go ahead for list 6 and standardize those by taking the square root. So the components are kind of like variation, then we take the square root of them to get us to standard deviation. So for list 6, I'm going to take the square root of list 5, and these are going to be the z-scores, which is pretty cool. So the second one, which was 28 more than expected, that sounds bad, right? But how do we know how to quantify that? We don't. Instead what we do is we think of it as z-scores, like more than 2 standard deviations above the mean would be considered unusual. So that was the most unusual with strawberry kiwi. So if they really were evenly distributed, we're leaning pretty heavy towards the fact that we think that more students actually prefer strawberry kiwi and that there actually really is a preference there. And so that might be enough just from that one to make the whole thing unusual, but maybe not, because the other ones were fairly typical. So we'll see. That's why we have to take them all into consideration. So we need to take the sum of list 5. So I'm going to go to second stat to list menu, or over to math, and then the fifth one is sum. So we're going to take the sum of list 5, which is going to give us a chi-squared statistic of 8.11. Now we had, let's see, 3 degrees of freedom, so it's going to be definitely a lower p-value than 50%, so we're definitely onto something, but to get the exact one, we'd have to go and do the CDF. So second variables, and we're going to go to the chi-squared CDF. So just like normal CDF, or TCDF, but now it's going to be a chi-squared CDF. The lower limit is going to be 8.011, I believe. The upper limit is going to be positive infinity, 999. Degrees of freedom are going to be 3 in this case, and then we hit paste. Alrighty, and so that gives us a p-value of basically 4.57 or 4.6 if we wanted to round, which would be, if we were testing that with a 5% alpha level, that would be statistically significant. So check the assumptions and conditions for the chi-squared test. Counted data, all of them were in counts, so counts the number of drinks each student purchased across 4 categories, so we're good to go. Independence assumption, each student's choice should be independent of the other, so we're good to go. We are expecting at least 5 in each cell, so clearly good there. And then if we're generalizing this across to basically all students, not just the ones we gather data on, but nationwide, then we need to make sure that we're sampling less than 10% of all the drinks that are sold, so we certainly are doing that. We'd also need to do randomization, so we need to make sure this is a random sample, not a convenience sample. So that would be another thing that I forgot to add there. Write your hypothesis. So the null hypothesis would be that they're evenly distributed, or that there's no preference for the drinks. The alternative would be that there is an association between them, so there actually is a preference, or that the drink preference is not evenly distributed. So calculate the p-value for the sum of the components for the chi-square test. We did that. That was the 8.012 or 117, 118, however you want to round it. If we use a significance level of 5%, well, we had a p-value, I think we said that was right here, so less than 5%, so that would be statistically significant. So out of 5% alpha, or basically being okay with having 5% false positives, we would have enough evidence to reject the null hypothesis in favor of the alternative, saying that we believe there actually is preference, and that the students do actually have a preference there. So on this one, for our model, we had 3 degrees of freedom, which would be our mean. That's the balancing point. The 3 minus 2 is 1. That's the mode, the most common one. So this is our model here. We had a chi-squared statistics sum of about 8. So that's the area under the curve there. So it's notice it's not like a normal model in this case. Alrighty. So next one, chi-squared for test for independence. As part of a survey, large students in a stats class were asked whether or not they ate breakfast that morning. The data appears in the following. So this is a test for independence because it's from one sample of one group in a contingency table across there. So you fit across 2 categories, whether or not you ate breakfast, yes or no, and male or female. And so you're going to fit somewhere within those 4 categories, and we want to see whether or not we think these 2 variables are independent of each other, if there's an association between your sex and whether or not you eat breakfast. There was a joke there from last year, I think. All right, so notice here we have our conditional table. We also have the marginal distributions as well, okay? If we're looking at degrees of freedom, by the way, since we really just have 2 by 2, there's only 1 degree of freedom. So for instance, if I tell you how many males ate breakfast, if you know the total, you can figure out how many males didn't eat breakfast. You could also figure out, if you knew the total of how many ate breakfast, you can figure out how many females ate breakfast. And then knowing how many were left over, you could also figure out how many females didn't eat breakfast as well. So there's really only 1 degree of freedom. There's only 1 cell that we would need to know in order to be able to fill in the rest of them, knowing the totals that we had anyway. All right, so let's go ahead and put this into our calculator. So we are going to list this out here as male yes, male no, female yes, and female no. So to be able to calculate the expected values, what we were doing is, if they were independent, we want to find what would the expected counts be for each one of these categories. So that can be a little bit tricky. So let me show you how we would do it. Essentially, we're going to multiply the the marginal probability of being male multiplied by the marginal probability of being or of eating breakfast. So we'll go to alpha x and put it in as a fraction. So probability of being male was 132 out of 331. And then multiplying that times the probability of eating breakfast, 191 out of also 331. Now, when I do this, it's going to give me a probability, but I want to go ahead and multiply that to get back to count. So I'm going to multiply it by 331. Oh, almost made a mistake there. So that would give me an expected count of 76.169. So I'm going to go ahead and go to clear all my list. And then go into stat and edit, and then for list 1 I'm going to put in so male yes, and then male no, female yes, and then female no. Okay, then for the expected amounts here, I'm going to actually type that in here. So that's going to be, so that's, we said 132 times 191 all divided by 331. Okay, I'm going to do the same thing here. So that's going to be, this was male no, so that's going to be equal to 132 times 140 divided by 331. And then this is female yes, so that's going to be equal to 191 times 199 divided by 331. And then female no is going to be 140 times 199 divided by 331. You might just notice some patterns there. All of those expected values together, if we add them up, should be the same as what we had here. Okay, so we're going to take our observations minus the expected. So this is going to be basically list 1 minus list 2. All right, and then we're going to take those and square them. So this is going to be equal to list 3 squared. All right, then we need to proportionalize those. So divided by their expected values. So list 5 is going to be list 4 divided by the expected values, which is list 2. So they're not all the same, so I do have to put it that way. And then I'm going to standardize those for list 6 by taking the square root essentially of those components, which are like variation. So that's going to be the square root of list 5. Okay, and that's going to give me the components. So the most unusual one was female that did eat breakfast. That was the one that was much higher than what we expected, the highest proportion. And that, but it was still just 1.36 standard deviations above what we expected, which is not that unusual. If I take the sum of the components, which is going to be the sum of list 5, I can actually probably go back up here because I typed that in somewhere. Yeah, the sum of list 5, it'll do it again. So that gives me a sum of list 5, which is the sum of all the components, to be a chi-squared statistic of 5.39 or 5.34. Now our degrees of freedom was just 1, so let me go ahead and go over here so we can kind of graph it out. And then what I need to do is go to second distribution. We're going to do the chi-squared CDF. The lower, I'm just going to paste this and then I'll type over it. Degrees of freedom was 1. Okay, and then I'm going to type that value in because I forgot what it was. So that's 5.339. Okay, there we go. So should be good. That gives us a p-value of 2%. So again, that is statistically significant. So we would have enough evidence to suggest that there is an association between between sex and breakfast. So if you are, apparently if you're female, you're more likely to eat breakfast than if you're male. So that's it. I hope you guys enjoyed that. Hopefully it won't be too long. The next 2 videos that I make on this, because we've kind of gone over the groundwork, should be a lot shorter. So I'll see you guys later, and I hope you have a good day.